Hello, so today we are going to do this problem called remove leaf nodes with a value. So the problem says we get a binary tree and an integer target, and we want to delete all the leaf nodes that have that value target. And so basically we want to delete all the leaf nodes with the given value target, but we also want to delete all the parent nodes that became a leaf node and that have the same value target. And so what this will look like with an example is, if we have a tree like this and the target is 2, we want to delete the leaf nodes that have value equal to target. And so we want to delete the leaf nodes that have value 2. And so we delete this one, we delete this one, right? And we end up with this tree here. And then after that, now after deleting this leaf node, this here became a leaf node, like the parent became a leaf node. And it has also the same value target. So that means we need to remove this also. So it recursively removes those that became a leaf node and that have value target. And so we remove this one too. And now we end up with this tree here, and we are done. So we remove all leaf nodes that have the value target, and then we check again the parents that became leaf node that have the same value target. We remove these two. So let's see how we can solve this problem. Okay, so let's see how we can solve this problem. So looking at the tree example that we had, and the target value was 2. So right away, looking at this, what we know we need to do is we need to explore leaf nodes first, right? So let's note that down. Explore leaf node first, because that's where we want to delete. So explore leaf nodes. Actually, let's word it differently. We want to delete leaf nodes. With value target, right? So which means we need to process all the way until we get to these leaf nodes and then remove them, right? So we remove them, which means here we will get something like this: 1, 2, 5, 2, 6. So after removing these leaf nodes, we need to go to the parent and check them. So then go to parent and check if it's a leaf node, if it became a leaf node. Plus has value target, right? Which in this case we have, because this node here has value 2, and it became a leaf node after we removed its child here. So also we should remove this one, right? Because that one has value 2. The other parent, which is 5, still has a child, and the value is still is not equal to 2, right? But this one we should remove it, and so we end up with this, and then we go back. So we go to 1 and check again, and 1 is not a leaf node, and the value is not target. So and from 5 we backtrack to 1 also and check that, right? So if you look at these here, what order are we using? So it's a good idea when having a binary tree to think about, okay, I know I need to traverse the tree, but what kind of traversal would help me the most in solving the problem, right? There are 3 types of traversals that we can do on a tree. There is the in-order traversal, and there is the pre-order traversal, and we have the post-order traversal. So what does each one do? So in-order traversal checks left first. So the left subtree, or the left node, and then the root, and then the right. Pre-order does left, right. Sorry, does and pre-order, so pre here means the root first and then the children after that. So we have root, and then left, and then right. Post-order means root last, and we check left, right, and then root, which means we will keep going left and then check the left of that until the last left node, the leftmost node, and then we back up, we go right until the rightmost node, then we back up to the root of those. And so you could see here, we check the leaves first in the post order, right? In all the other ones, we check the root first or the root second, but the right becomes last in the in order. And in the pre-order, the root comes first, which means after we remove the leaf nodes, we won't go back to the root. So this one won't help us because in the problem description, we want to go back to the root of each child after we possibly remove it to check if it became a leaf. So this one won't help us. This one either won't help us because the right node, we check the root before it. So if we remove a leaf node on the right, and then we would have already checked the root node. And so if that root node became a leaf node after removing right, we won't check it. So this one won't help us either. But this one will, because we check both leaf nodes, both children. And if we ended up removing both, for example, and the root became a leaf node after that, and it has value target, we will be able to remove it. So this one is the one that will help us the most, which means we need to do post-order traversal, which means we need to explore left, explore right, check the node, remove it if it has value target, and then go back. We will go back up the stack and check the parent, right? And so what this would mean here, removing, there is just one thing to clarify here. Removing would mean if we use a recursive function, it will be enough to return none, and then have the parents just assign those by doing maybe root.left equal to the recursive call and root.right equal to the recursive call. And by returning none, we will just, the root, if we remove its left node, it will, and maybe remove its right node, it will become a leaf node, right? So let's just write this down. So this here is delete leaf nodes, the function. So let's call it that, def delete leaf nodes, and we get as input the root and then a target value. And what we want to do first is, well, what if we got as input just a none node, a node that contains nothing? So we need to check that edge case first. So if not root, which means root is none, we can just return root. The second case now is, since we are doing post-order traversal, we need to traverse the root left. We need to delete the leaf nodes that have value target on the left side first. So to do that, we just assign, as we said here, root.left to the result of the recursive call for self.delete leaf nodes. And this would be on root.left. And value target. And then we do the same thing for root.right. So this is the post-order traversal, left, then right, then root. So we delete leaf nodes on the right that have value target. And now we check the node itself, right? And so to do that, we just say, okay, we need it to be a leaf, which means it needs to have a nil root left, a nil left, and a nil right. So to check that, to check it's none, we can just use either, we could do root.left is none, just to be super clear, and root.right is none. And we need to make sure that it has value target. So, and root.val equal to target. So if this is the case, then we want to remove it. And removing it, we can just return none instead of returning the node. That way, if we go back up, either it was the left child and its parent left, we will assign to that none, or it was a right child and its parents right, we will assign that none, and that will be equivalent to removing it, right? And that's pretty much it for the recursive call here. So the only thing that we can change a little bit here is that this check for root.left is none and root.right is none, just checking the leaf. Just to give you different ways of doing it, we can also do it in a way where we say if not root.left, which is equivalent to checking that it's none, and is not root.right. Another way, slightly different way to do it is that, well, since these are two different nodes, they won't be equal unless they are none, right? So we can just say root dot left equal to root dot right, and this would be valid only if both are none. Okay, so this is equivalent also to checking that it doesn't have a left child or a right child. Now let's take a look at the time complexity and the space complexity. So since we are doing a post-order traversal here, we are checking both the left, right child and then the node itself for every node in the tree. So what this means is that we will explore the entire tree, which means that our time complexity here is O of n. And in terms of space complexity, how many recursive calls we will do? We'll do as many as the height of the tree, right? And so we will put on the stack O of n. Before unwrapping, we will put the left and the right, and then we'll do that for the entire tree. So for the space complexity here, we are doing O of height of the tree space. This is the height of the tree. So the main insight of this problem is when you have a binary tree that you need to explore and you want to explore it recursively, it's a good idea to figure out which one of the traversals that we can do that will help us solve the problem better. Because here, if we used any other ones, we would have problems with our recursion here. Yeah, so let's write this down and run it on an example. Okay, so I just typed here the solution that we just saw in the overview here, where we check that the root is not none, and we return it if it is, because there is no need to explore. We do the post-order traversal, we explore the left side, the right side, and then we check the node itself if it's a leaf node, and then we check if it has value target, then we remove it by returning none for it. And so the tree in that case would look like, for us, it looked like this. So we have 2 and child 2 here, and we delete the leaf node of value 2 here, and it looks, we should remove all the leaf nodes with value 2, including the parent. And so you can see we end up with just 1, 5, 6, as we saw in the original example. So this works fine. Yeah, so that's it pretty much for this problem. The only small change we can do, as I mentioned, is we can check if root.left equal to root.right. This would be the same at checking that both are none, or we could also just do is, which just checks the same thing as the equality, and both work fine. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one.